The emergence of the Type B unmanned combat aerial vehicle represents a major shift in the way air power may be projected and managed in future warfare. It reflects a deliberate effort to move beyond traditional unmanned systems, which have historically been relegated to surveillance, reconnaissance, or limited strike missions. Instead, Type B is shaped around a very different vision, one that involves stealth, speed, endurance, and potentially autonomous decision-making in contested environments, including direct engagement with enemy aircraft or targets defended by sophisticated air defense systems. The physical design of the aircraft tells a great deal about its intended role. It has no vertical stabilizers, a feature that immediately sets it apart from most conventional aircraft and even from some stealth aircraft. The elimination of tail surfaces is a major step in reducing radar cross-section, especially from the rear and side aspects. This choice likely required the development of a complex flight control system, possibly using software-driven control surfaces to maintain stability and maneuverability, especially at low speeds or during sharp maneuvers. Such systems demand a high level of integration between aerodynamics, sensors, and flight computers, suggesting a significant advancement in control technology. The wing itself is sharply angled with a planform that blends into the main body. This diamond-shaped or modified delta configuration is often associated with high-speed performance and aerodynamic efficiency. It also provides a large internal volume, which can be used for fuel, internal weapons bays, or electronics. The lack of external hardpoints further supports the idea that the aircraft is meant to carry all of its weapons and mission systems internally to avoid creating radar reflective surfaces. The air intakes are another key indicator of design intent. Positioned on the sides of the fuselage and shaped without traditional inlet ramps or moving parts, they follow a diverterless configuration. This reduces complexity and maintenance, while also helping with stealth by smoothing the aircraft's external lines and reducing the number of seams and edges that could reflect radar. These intakes are optimized for airflow in supersonic regimes, which implies the aircraft is designed to exceed subsonic speeds and could potentially reach high transonic or supersonic velocities. High speed allows it to rapidly penetrate defended airspace, reposition during engagements, or evade threats. The single-engine configuration appears optimized for a balance of performance and fuel efficiency. The engine nozzle is serrated, which is a relatively advanced feature intended to scatter radar waves and reduce infrared emissions. While this may not match the full rear aspect stealth performance of flat or embedded nozzles, it suggests an attempt to maintain stealth characteristics without significantly compromising engine thrust or adding complexity. This may be an interim step, with future variants possibly incorporating more sophisticated exhaust designs. One of the most telling features is the presence of a chin-mounted optical system. This system is placed beneath the nose, likely housed in a faceted window or fairing that blends into the aircraft's contours. This position gives the sensor a wide field of view, allowing it to track targets visually, identify threats, or aid in targeting. These sensors are often passive, which means they can collect data without emitting signals that would reveal the aircraft's position. A system like this could be essential for air-to-air identification, navigation in GPS-denied environments, or target acquisition in strike missions. The aircraft's surface shows minimal protrusions or unnecessary structures, a hallmark of stealth design. It suggests that radar-absorbent materials and coatings are applied across its skin, and that special attention has been paid to managing how the aircraft reflects and emits energy. The minimal surface seams, embedded antennas, and smooth transitions between body parts support the idea that the platform has been designed from the ground up for survivability in electromagnetic threat environments. The operational concept behind such an aircraft is likely multifaceted. It may be capable of operating as a standalone fighter-like system, engaging in combat independently or semi-independently, using onboard sensors and computing to make tactical decisions. It could also function in a networked environment, where it receives data from other aircraft, ground stations, or satellites, and is tasked remotely by a human operator. This flexibility would allow it to operate in various modes depending on the threat level, mission requirements, and rules of engagement. The ability to function independently in combat is especially relevant for missions involving high risk. Sending a crewed aircraft into an area dense with enemy radar systems, long-range missiles, or electronic warfare threats exposes the pilot and the aircraft to high danger. An unmanned system removes that risk. If it is shot down or disabled, the loss is strategic and financial, but not human. This changes the calculus in planning operations, enabling more aggressive postures or actions that would previously have been too dangerous. If the Type B is also capable of operating in teams with manned aircraft, it may extend the sensor and weapons range of those aircraft. For example, a manned fighter could remain at a safer distance while the unmanned aircraft flies forward, identifies or engages targets, and transmits data back. This distributed approach to combat operations increases survivability, enhances battlefield awareness, and creates more complex problems for an adversary trying to counter multiple systems simultaneously. In addition to direct combat roles, the platform might be configured for supporting functions like electronic attack, communications relay, or jamming. The internal volume and stealthy design make it a potential candidate for specialized payloads that allow it to support other aircraft or ground forces in complex operations. Its autonomy would allow it to fly missions that require extended durations, precise timing, or continuous monitoring without fatigue or the limitations of a human pilot. Autonomy is a critical factor in this aircraft's potential value. While remote piloting remains common in current drones, the latency, bandwidth requirements, and vulnerability to signal jamming limit how well it can function in denied environments. Autonomous or semi-autonomous systems, by contrast, can navigate, recognize threats, and carry out predefined actions without waiting for direct commands. This opens up new tactical options, such as launching swarms of drones that react to battlefield changes in real time, coordinating amongst themselves and adapting their behavior dynamically. The development of a system like Type B also reflects an organizational and doctrinal shift. Integrating such advanced drones into military operations requires changes in training, logistics, command structures, and tactics. Pilots must be retrained to work alongside unmanned systems, commanders must learn how to assign missions to machines with varying levels of autonomy, and support infrastructure must be built to maintain and upgrade these systems. The investment in all of these areas signals that this aircraft is not an isolated prototype, but part of a broader transformation in how air operations are conceived and executed. Although no official confirmation has been made about its operational status or combat readiness, the existence of the aircraft and the detail visible in its design suggest it is far beyond the early conceptual phase. Whether or not it has flown, it is clearly a platform that has received significant resources, engineering focus, and likely real-world planning for integration into future combat forces. Its development timeline, deployment strategy, and eventual role will depend on testing results, production capacity, and doctrinal acceptance. As with any advanced system, its success will depend not only on its technical specifications but also on how well it can be maintained, adapted to different missions, and operated under real-world conditions. The Type B represents a new level of ambition in unmanned systems, moving from tools of support and observation toward full participation in high-intensity warfare. Its existence marks a new stage in the evolution of air combat, where the boundary between manned and unmanned, between support and primary combat roles, is no longer clear-cut. The long-term implications of such systems are profound, and they will play a central role in shaping how air power is projected and contested in the years ahead.